Alright, good morning everybody. Let's start off with a warm-up today. Please do this in your warm-up book and then I'll give you the answers or something like them at the end of the lecture. Draw the electron cloud model of fluorine, write the electron configuration of calcium, and then write down what the definition of a continuous spectrum of light is, as well as a non-continuous spectrum of light. So go ahead and do that in your warm-up books, and then come back to this video when you're done with your warm-up. So far we've covered the s and p orbitals of different atoms, and you notice I've drawn the 1s here and the 2s, and this would be all the 2p's here. And now that I've shown the s and p orbitals once again, I want to go a little bit deeper. This won't be on the test, but it's really nice to know. What happens when you get deeper down the periodic table and the atoms become quite a bit larger is that you have to go beyond the s and the p orbitals into what are called the d and the f orbitals. These are in the center of the periodic table. These are where there's tons and tons of metals. And what you basically have to be thinking about is, remember, the electrons are going through a choice decision. They'd like to be as close to the nucleus as they can get, but they have to be as far away from all the other electrons as they can get. So if you look at this picture of the s's and the p's, you'll notice that there is some space here, there's some space here, space here, space here. There is some space left over, and that creates the d orbitals. Here are the d orbitals, and you can see how they fill up all the empty space that was still available between the p orbitals and the s orbitals, and they have very, very funky shapes. And remember, these are electron clouds that represent where the electrons are 90% of the time. They can go outside of the space. Notice there are 5 d orbitals. They can each hold 2 electrons for a total of 10 electrons, and that equals the 10 transition metals. Now, believe it or not, if you superimpose these along the s's and the p's, there would still be a little bit of space left over. And if you found that little itty bitty bits of extra space for the electrons to go, that would then create the ridiculously amazing f orbitals. These are the atoms right at the bottom of the periodic table. These create very limited space that remains between all the other orbitals. You can see how incredibly complex these electron clouds are. There are 7 of these. They can each hold 2 electrons, and so that makes a total of 14 electrons, which is the very bottom line and the last group on the periodic table. Alright, we have now finished all the electron clouds. Remember, the shapes that you're responsible for are the s orbitals and the p orbitals. I now want to talk very briefly about electricity because it's such an important thing when you talk about light. If you didn't already know it, there are 2 types of electricity, and as my son Jason would tell you, this is the amazing band AC/DC for alternating current and direct current. Alternating current means that it goes back and forth. It goes zzz, 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 back and forth very rapidly, whereas direct current means that it's going only in one direction. All the current in your house is AC, alternating current, which means it's going backwards and forwards about almost 200 times per second. So the frequency of the electricity in your house is almost 200 times per second, somewhere between 160 and 220, depending on where in your house it is. So it's going on and on, on and on, on and off very quickly as it goes through and your house. So when you plug in the power cord for your computer, here I'm going to grab one, or for your cell phone, they almost always have one of these little funky things. And this is a converter. And this converts AC power to DC power. Because as you might imagine, you can't have your computer turning on and off 200 times per second. It's not capable of doing that. So your computer and your phone and any other type of electronics has to run off of direct current so that it's always on and doesn't turn on and off all the time, because computers obviously can't do that. So this would be a transformer that's transforming AC current into DC current, so I can plug it into my phone, and then my phone will charge up with extra electrons. Speaking of current, let's make sure we understand what current is. Current is a flow of electrons. So any time that electrons are flowing, you could consider that current. And so when you have electricity flowing through a wire, it means electrons are flowing through that wire, and that's what you're putting back into your phone to charge it is electrons. Energy is electrons. All right, so now that we know about AC and DC power, we can begin to talk about light, because light is very cool. Now the lights in my house, for example, are running off of AC power. So that means that the flow of electrons is going on and off very rapidly, and believe it or not, these lights are turning off about 200 times per second. You can't see it because it's so rapid that our eyes don't see it. If you've ever noticed a light that starts to flicker, that means the frequency of the light is going down, and the light is getting old. It's probably going to burn out pretty soon, and the frequency has become low enough that you can see the light turning on and off. The younger you are, the higher frequency of lights you can see, so you can probably see when lights burn out faster than I can, and I hate it when lights are turning on and off because the frequency is going out. So the electricity is coming into these lights 200 times per second on and off. Now we need to make sure we understand what it means to make light. Light is pretty incredible. We've talked a great deal about the properties of light. Now we need to make sure that we understand how light is made, because there's a lot of light around. We've talked about all the different types that come from the sun, but we haven't talked at all about how they're made. So here's how it is. Now that we finally know what atoms look like, and we know there are different energy levels for atoms, we can finally get into understanding how light is made. And the way light is made is the following. When you give energy to atoms, whether it's in the form of heat or electricity, or even in the case of light, because light is energy, if you give energy to an atom, something spectacular happens to the electrons. And for example, an electron that's in the energy level 1, when it gets the right package of light, which is called a quanta or a quantum of light, and everything we've been talking about is quantum mechanics. When you're given energy to an atom, the electrons in lower energy levels can jump out to higher energy levels. This happens almost instantaneously, and this is called becoming excited. So when an electron becomes excited, it takes in a certain package of energy, and it bounces out to a higher energy, for example, going from energy level 1 to energy level 3, and then it very, very, very rapidly returns to where it started from, which is called the ground state. And as it returns to the ground state, it gives off the energy that it had gained as a photon of light. And this is how light is created. Whenever you give energy to atoms, the electrons bounce out to higher energy levels, and as they very rapidly return to the ground state where they started off, they give off that energy that they gained as a photon of light. And as we've already learned, there are many different types of photons of light. Microwave light, UV light, visible wavelengths of light, gamma rays. All these are different jumps of different electrons. Whenever an electron bounces from energy level 2 out to any other energy level, and then back again, those create visible wavelengths of light. So the visible wavelengths of light are created when electrons go from energy level 2 to any other energy level. And then all of the different types of light that we've talked about are different jumps. From energy level 1 out to something might be one type of light. From energy level 3 out to other energy levels would be a different type of light. So each of the different lights corresponds to a different energy, a different wavelengths, a different frequency, and in the case of visible wavelengths of light, a different energy, which is a different color. Now, going along with this amazing thing, which I'm going to say one more time, when you give energy to an atom, it doesn't matter whether it's a gas or a metal or any type of atom, amazing things happen. That energy can be heat, it could be light, it could be electricity, any type of energy. When you give energy to an atom, the electrons become excited, they jump out to higher energy levels, and they very quickly return to their ground state, and along the way they give off a photon of light, and there are lots and lots of different types of light. And if you're the sun, for example, or a star, you're making every different possible type of light there is. If you're a light like the one in my kitchen right here, the only type of light you're making is visible wavelengths of light. And as we've already talked about, If you make lots and lots of different visible wavelengths of light mixed together, then our eye interprets that as white. Now, finally here, we need to talk about some very important equations that go along with light. And these are two very biggies, and you're going to need to memorize them. The first one I've already given you. It's the frequency is the speed of light divided by wavelength. And you need to remember the symbols, you need to remember the different things. Remember, I will give you the speed of light, which is 3 times 10 to the 8th meters per second. The second one involves energy. And energy is the frequency times a funny constant called Planck's constant. Planck's constant. And I will give you this also. Planck's constant, believe it or not, is equal to 6.626 times 10 to the negative 34th joule seconds. I know that's hard to believe, but it's the truth. Now, finally, there's one last way that you can look at this equation. Instead of being energy is frequency times Planck's constant, it's also the speed of light over frequency times Planck's constant. And so this is another way that you can represent. I would suggest you memorize this equation and you memorize this equation and what all the symbols mean. All right, now that you have been introduced to these two awesome equations, it's important that we get back to calculators for just a second. Whether you have a beautiful Sharp calculator or a Casio or a TI, you need to be able to work with exponents. So what you're looking for is, for example, on my Sharp calculator, the button I'm looking for is called EXP for exponent. On my Casio calculator here, I have times 10 to the x. It's down here in the bottom in the middle, which is very common for Casios. Sometimes you'll see lowercase e twice, and sometimes you'll see uppercase e twice. Get your calculator out right now and find out which button you have on your calculator. Now, once we have that figured out, I'm turning my calculator on, and I'm now going to figure out how do I change 700 nanometers into meters. And I will tell you the conversion factor is that 1 meter is 1 times 10 to the 9th nanometers, and I will give you this conversion factor on the test. So, the way that I would do this is I would go 700 divided by 1, 10 to the 10x, 9 equals 7 times 10 to the negative 7 meters, because nanometers cancel out. Make sure that you found the appropriate button on your calculator and you know how to use it, because you're going to need to be able to do that for these types of problems, which we'll practice the remainder of the week this week.